A title page. First thing I would do is I check the guidelines. Does it say title page, yes or no? I don't think it says anything about a title page. If something's not addressed in the guidelines, that means it's up to you. Okay? You can't read my mind. I can't say, hey, I didn't want a title page. But there's nothing in the guidelines. Okay? There'll be many questions like that. If the guidelines don't address it, it's up to you, your choice. I do want you to develop your own style. I'll give you a few guidelines that you must follow if you want. Otherwise, make it how you think is best. Okay? A couple other people have asked similar questions, and I gave similar answers. Okay? Up to you. I don't want to make everything so scripted that you have to just do this, do this, do this. You want to develop your own style. And I appreciate seeing different styles. Okay, acid-base chemistry. Here we go. Y'all ready? Okay, you know your acid-base mechanism? Hugely important. Understanding arrow movement. Okay, what does each arrow mean? Hopefully everything is explained there and you'll be able to use it. I would have used it over here. Okay. We'll eventually show the answer there, but hopefully you've already maybe got an answer there, yeah? Okay. So that's hugely important. Okay, we're looking at, early on here, how to determine what's the stronger acid. We looked at the H2O versus HF, and we said HF is the stronger acid, but why? We need to look at the conjugate base. Today, and organic 2, you look at the conjugate base when you're determining how strong something is. What's the conjugate base? You guys got to be able to show conjugate bases. Too many times I see answers and it's not the conjugate base. That's the first thing, okay? So, then you compare your conjugate bases and you ask which one is more stable. And here the answer is F minus because it's electronegativity underlined there. F can handle being minus more. It likes being minus more. Thus, HF is going to be more willing to act as an acid and become the conjugate base compared to water. You got to look at where you're going. F minus is more stable. Let's make this a little smaller. Okay, let's get it in gear here. Which is a stronger acid, water or ammonia? What do we need to consider?
Conjugate base.
Conjugate base. What's conjugate base of water? Hydroxide. We've already showed that. Conjugate base of ammonia. NH2 minus. Okay, 2 lone pairs, right? Okay. Which is more stable? What can be your argument? These are different atoms. The charge on oxygen, minus on oxygen, or nitrogen. Which can hold the charge better, likes it better? Oxygen, because it's more electronegative. This is more stable, thus water is more willing to act as an acid and become the conjugate base. Water is more acidic. Now you may know ammonia as a base. Actually, ammonia is actually a base. It can be an acid. Just about anything with an H can be an acid. All depends on what type of base you got. Which is more acidic, water or methane? Well, what's the conjugate base over here? CH3 minus. Okay, which is more stable? OH minus or CH3 minus? Electronegativity. Oxygen more electronegative. Carbon we're moving more to the left. Carbon, we will see carbanions. Carbon doesn't love being minus. Okay? That's the least stable anion we've showed thus far. That's less stable than this. Which is more stable, C minus or N minus? Otherwise, just
N minus.
Yeah, this is worse than N minus. Water is more acidic. Okay? You rarely see a CH as acidic, because rarely is a C minus stable enough to be readily formed. Exceptions always. Okay, these two are kind of group together, electronegativity, size of the atom, which is more acidic, HCl or HBr? What do we want to consider? Conjugate base. Okay? Conjugate bases are Cl minus and Br minus. Which one is more stable? Well, if you look at electronegativity, Cl minus is more electronegative. Up and to the right, more electronegative. But that's not the right answer here. Based on electronegativity, you would say HCl is a stronger acid. HBr is actually the stronger acid. We know that from experiment in lab. Those pKa's can be determined. Why? What's the rationale of the argument? The answer here is because Br is, well, apparently that means Br is more stable. Br minus is more stable. If HBr is more acidic, that tells you that Br minus must be more stable. The question is, why is Br minus more stable? Not because of electronegativity, but because it's bigger. And the charge is spread over a bigger nucleus, a bigger atom. And if the charge is more spread out, that's better, and that actually beats electronegativity. Okay? So you have to be careful, because if you start going diagonal on the periodic table, sometimes these two get mixed and you get the wrong answer. Size, going straight up or down a group, size beats electronegativity. Okay? Which is more acidic, HBr or HI? Well, what do we want to consider? The conjugate bases. Br minus or I minus? Why I minus? Br minus is more electronegative. But I is larger, and right up and down a group, larger is the biggest effect. The most important effect going right up and down a group. Okay? Which is more acidic, H2O or H2S? Which is more stable, OH minus or SH minus? But oxygen is more electronegative. But sulfur is larger, and sulfur is more important going up and down a group. H2S is more acidic, okay? Because HS minus is more stable. We're considering the conjugate bases really, right? Okay, down here, what's the most acidic hydrogen in this compound group? We got OHs, SHs, NHs. There's also CHs there, right? CHs are least acidic. We kind of said that up above. A C minus is going to be the least stable. The question is, where would you rather form a minus at? We got three things here. How to do this? Let's go straight across or straight down. Diagonal, see, into S is diagonal. Let's go straight across or straight down. What about straight across? Which is more acidic, OH or NH? OH, because O minus is more stable than N minus. Because O is more electronegative. So that ain't the answer. Now compare this to this. Which is more acidic, OH or SH? SH. Now we're going straight down, and size beats that. That beats that. The answer is the SH company, the SH group. Straight across or straight down. If you had done diagonal, you could have like, well, which is more here? And it becomes a little blurry, not as clear. Okay? Number 2, 1 through 4 was listed on the previous slide. Number 2 is inductive effects. They're very important. Which is more acidic, this alcohol or this alcohol? What's the difference? There's an F, fluorine added out here on the end. First off, what's really I mean, F is not acidic. Okay? What do we really need to look at here? CHs. It's really, let's look at the OHs, because within the compound, the OH is most acidic. Within this compound, the OH is most acidic. But now let's compare two different OHs. And it turns out that this one is more acidic. Why? Well, let's look at the conjugate bases, which are these, right? What does this F out here do? The F is electronegative. That means it pulls electron density towards its nucleus. Okay? This minus out here is being pulled this way. Now, the F pulls the bond between F and C, but it's kind of like tug of war. If I'm pulling here, I can make you partial positive, but I'm also pulling over there as well because the effect is multiple bonds. And so it pulls here, but it's really pulling all through here. So this electron density here, you can't think of it as just sitting out here. That electron density, electron cloud is pulled this way, away from the oxygen, and that's a good thing. Because the charge is not sitting just right there localized in a single space. And this is called inductive withdrawing. Stabilizes the minus. Here's a term that I'll use more and more going forward. How do you stabilize a minus? Do you push electrons towards it or pull away? Things want to go more towards neutral. If you're a minus, pushing electrons towards you is not a good thing. That's not going to make you more stable. If you're a minus, I don't make you more stable by pulling electrons away from you. And that's what the F does here. Pulling away, inductive withdrawal stabilizes this. Does this have the F? No. Does this have anything? No. We can actually state that these are just plain carbons out here. And it's very important to know that an sp3 carbon is actually an electron donating by induction. An sp3 carbon pushes electron density. That's not going to help this oxygen minus. That's going to hurt it. So, the question is, which one of these is more willing to become the minus? And act as an acid. Let this be an acid for this one, because it's becoming more stable compared to this. That one's more willing to act as an acid. That's the most acidic. Inductive donation by the F next to, which is more acidic. What's the difference? An extra sp3 carbon. That's the difference. What does an sp3 carbon do electronically? It donates by induction. So we can say this is extra donation. Okay? We're considering the minus here, right? I'm not going to draw it every time, but we're considering the conjugate base. Is this pushing going to help that conjugate base be happy and stable? No, you don't stabilize a minus by pushing electrons towards it. So that's going to hurt. That's bad. See, up here, this was good because it was pulling this way. The sp3 carbon donate. That's bad compared to this, so this is the winner. Because the other one's bad. We're considering the minuses here. Right? How do you stabilize minuses? Do you donate, push electrons towards them? No, that's bad. Next, which is more acidic? This has branching here. With branching, it's like 3 pushing. sp3 carbon donates, sp3 carbon donates, sp3 carbon donates. You know, you could say this donates. This is said to have more donation because the branching, it doesn't matter how long this is. You could say, well, we got 10 carbons over here and maybe 3 over here. If it's one long chain, it's only like 1 donation. But if it's branched, each line here is like a different donation. And so you got kind of 3 alkyl groups donating. Alkyl, methyl is an alkyl, methyl, ethyl, propyl. Alkyl, right? 3 sort of, it's like 3 lines of donation. This is only 1 line, no matter how long it is. So which is going to be better if we're considering the O minus? The first one. First one. That one's triply worse. Again, we're really considering and don't do this on your handout because you'll get it all, okay? We're really considering the minuses, right? Triple donation hurts them. And thus, the original OH compound is not as eager to become minus. This one's more acidic. Down here, which one's more acidic? What's the difference?
Fluorine.
What does fluorine do electronically? Pull. Inductive withdrawing. What does chlorine do? Oh, so what's the difference? One pulls more than the other. Which one is more electronegative? Fluorine, up and to the right. Fluorine is more electronegative. This one pulls more. So you can sort of make it, heavier. It's pulling more. The F is going to stabilize the O minus more than the Cl will stabilize the O minus. Inductive effects. Which is more acidic, this one or this one? What's the difference? Fluorine's further away. Now, if you're playing tug of war, it doesn't matter how far away. The rope is the rope, and I can pull here and affect something 10 miles away, like a lone train. So my analogy of tug of war doesn't quite work here. Here, the further away the group is, the F is, the effect does diminish. Okay? The electron withdrawing nature, inductive withdrawal of the F is greater here. It's further away here. We are considering the minuses, right? And we're asking which is more stable. This one, because the withdrawing group is closer. As the inductive withdrawing group gets further away, the effect diminishes. All right? So that one's more acidic. It's more willing to become the O minus because the F is closer there to help pull the electrons away. These are examples of what? Inductive effects. What is inductive effect? Pushing or pulling through single bonds. Once we get to pi bonds, that's going to be called resonance effect. Single bonds, okay? Pulling through single bonds. Very common and important way of sort of influencing the electron density within molecules. Of course, if we had 3 Fs, that would be even more stable than if we only had 1 maybe, right? Because that's 3 pulling, that'd be good. Where here, 3 pushing was bad. I mentioned that because sort of a CF3 group is kind of very common. This chemistry here we're looking at, these effects, we're looking at them in terms of acid-base. They're going to be just hugely important throughout organic chemistry. We start reactions and everything, okay? So they're introduced here, but they impact many things in organic chemistry. Inductive effects, but also resonance effects. Okay, which is more acidic? This alcohol or that carboxylic acid? Want to consider the conjugate base, right? And we can say, what's out here inductively? That's just all donations, right? Yeah. There's nothing withdrawing. sp3 carbons. What's over here? Well, this oxygen pulls, so we got kind of a dipole that way. This is donating. This might give you your answer because that oxygen is kind of pulling away from this oxygen. It's not straight away, but if you just kind of draw a withdrawing group arrow like this, it's pulling this way. And you might say, well, this is more stable because of this withdrawing, and you would be right. That is more acidic. But the answer is not induction here. The answer is resonance. Okay? Resonance. And there's many ways to look at this. You can read there. It's clearly what I think is important, but let me give you more of a different look than what is written. Okay? More and more I see this as an important consideration. What's the hybridization of this oxygen? sp3. Okay? 4 regions. Lone pair is, each lone pair is in sp3 because an sp3 only mass sp3 type orbital. Over here, what's the hybridization of this oxygen?
SP2.
sp2, yes. Why?
The one of the low period points to
Because anytime a lone pair is next to a p orbital, does this carbon have a p orbital?
Yeah.
Yes, it's sp2 with a p orbital. Okay. We can even draw it in. You see the pi bond over here? That's the pi bond. One electron makes a pi bond. Well, one of these lone pairs we're going to put in a p orbital. And we're going to say that oxygen's sp2, right? And if we graph it, we're saying it's sp2. What type of bonds do you see the oxygen making?
sigma to carbon.
Sigma bond to carbon. And it's got 3 lone pairs. 2 of them are hybrids, and 1 of them, though, is in a p orbital. Why? So the p orbital can interact with the p orbital next door. And this is a good thing. Orbital interaction is a good thing until we get to one place where it's bad. Generally, it's good. And when this thing acted as an acid, it had 2 lone pairs here, now it has 3. It took on an extra lone pair. And in this case, the extra lone pair is conjugating with a neighboring p orbital. That's a good thing. Is one of these lone pairs conjugating with a neighboring p orbital? No, it's not. So it doesn't have the good thing. And the take-home is, this anion, this oxygen anion is not resonance delocalized. There's no resonance here. Over here we do have resonance. And what is resonance? Resonance is p orbital overlap. And we will build upon that definition. And if you have that, if you can put the extra lone pair in a p orbital, that's a good thing. It's going to make this anion more stable than that one. Thus, this is more acidic than that. This is more willing to become the anion. Okay? Resonance, conjugation. We'll start drawing resonance structures. Okay? There's no way for me to explain all of this fully in the time that we can commit to it here. I'm giving you an overview, intro. You got to read. You got to read my handout. You got to work problems. Okay. Another thing we'll do though is do resonance structures. What is that? That's just a different structure where all we have moved is pi electrons. We can move these up. That would give us this structure. Resonance arrow. I don't know that we mentioned that before. Double-headed resonance arrow important. Showing a different resonance structure. At this point, these electrons could move in here. What does that arrow mean? They're falling in to make pi bond. And we can get to this structure. And both of these structures are very valid. The true structure is actually a blend. But look at this. In this case, is the charge sitting just on this oxygen? No. What we see is the charge can also be shown on the other oxygen by resonance. And this is called charge delocalization. And when you're doing resonance, the true structure is actually a blend of these that we can draw like that. The true structure is actually something like this. This is a bond and a half. We blend together our structures. This one is not as good because there's 3 charges. One charge is better. So let's just consider these 2. Single bond here between this C and O. Double bond. What's the average of single and double? 1.5. And that's what I'm illustrating here. We've got a bond and a half between the C and the O. What's the average between double and single? Also 1.5. It's a bond and a half. 1.5 a bond. What's the average of minus and neutral? Half minus. That's why I got a half minus here. What's the average of neutral and minus? Same thing. This is a blend of our resonance structures. This is called your resonance hybrid. Another way to look at resonance. It also shows that the minus is not sitting just on this oxygen. The minus is spread to other oxygen as well. The charge has been spread out by resonance. So that's another way to make the argument of resonance. The most simplistic way, though, see, we have to learn how to draw resonance structures. We have to learn what a hybrid is. That's part of what we have to learn in resonance. But I think if we go back to what I first said is the extra lone pair here is sitting right on oxygen. It's sp3. But over here, the extra lone pair is conjugated. Back to what we said earlier. And if you can see that it's conjugated, that kind of gives you your answer at this point. You have to build upon full resonance description. And guess what? We're not going to officially cover resonance till test 3. Okay? We build, we talk about it. Unless you want to cover it all during test 1, like it's done in many classes. I think it's too early. Let's keep working at it, though. Okay? Question?
I was wondering if you scroll down a little bit, there was for the partial charge of the carbon in the middle resonance structure. Does that have to be noted in the final product as well?
Well, again, it all depends on what you're doing. I consider this a pretty bad structure. There's a little bit of partial plus on the carbon because neutral, it shows a little plus. Yeah, that makes sense because it's bonded to 2 oxygens. A carbon bonded to 2 oxygens would be a little partial plus, right? Yeah. Okay. Down here, I skipped the middle one, went directly to it. Okay. Again, you're not going to learn resonance here in 5 or 10 minutes we talk about it. All right? We got that? Let's look at another example, which is more acidic. This compound, which is called succinimide, by the way, or this alcohol. I'll give you pKa's based on pKa, which is more acidic. This one, right? Or pKa more acidic? Okay, good. Why is this more acidic? What's your argument?
Resonance, the electrons are going through the ring.
Which is, would you rather have minus on N or O? O. Based on what argument? Oxygen is more electronegative than nitrogen. We're going right across, right? Rather have a charge on oxygen? Minus on oxygen? Yeah. But then that should be more acidic. It ain't. Why is this more acidic?
Because of the electrons are going through the ring.
It's because of resonance. Let's look at the conjugate base. Conjugate base is that. What's the conjugate base of the alcohol? Okay. It's got a kind of an extra lone pair. Are any of them? Are any of these lone pairs doing p orbital stuff?
No.
No, this is sp3. There's no p orbital here. What about this one? One of these doing p orbital stuff?
Yes.
Yes, p orbital here and there. It's got 2 p orbitals beside it. So one of these lone pairs is going to be in a p orbital. The other one will not be. And it's interacting with that p orbital and it's interacting with that p orbital. It's got conjugation on both sides. Lots of resonance here. We could go through the same type of argument. We're not. But this should give you the answer. The question becomes, which is more important? Charge on more electronegative atom or all this resonance? Well, this tells you that all that resonance is more important. That's what made that more acidic. Okay? Yes? This is an example of how resonance can be more important than electronegativity. And often it is. Question?
Isn't the OH alcohol less acidic because isn't the alcohol less acidic because the carbons are also pushing electrons towards it?
Well, I mean, that doesn't help, you know. But you got to have some carbons or it wouldn't even be an alcohol. I mean, yeah. Question?
You said earlier that there's 2 sides of conjugation. Say that
No, just one. Just one. You want to put it in also in a p orbital? If you did, it would have to be like this, perpendicular to the first one. And if it's perpendicular to the first one, there's nothing next door to overlap, because the one next door is already interacting with the first one. Okay? Yeah. I mean, if you had two next door and the other one was perpendicular, only one. But one conjugating is better than over here because that has none conjugating. Right? That's actually because there's two next door. If you only had one next door, don't do this. If you only had one next door, this pKa would not be as low, and it would actually be more like 18 or 20. Okay? You don't need to know that because it's the bigger thing here. I mean, I gave you pKa's and we started with that, and then we said, okay, what's the explanation?
What if you were comparing two compounds and they both have resonance?
There's many questions like that to consider. Yeah. You would have to look for some other argument, right? They both have resonance, then that ain't going to be your answer to what is different about it. If you can find an example, let's look at it. I can show you many examples. Yeah. Each example we look at, let's learn something from it. And okay, next is, well, I'm going to say important again. All these are important in many cases along the way. Hybridization effects. Let's look at these CH compounds. We said CH compounds typically not that acidic. It still can be, though. The acidity here is this SPCH is more acidic than the SP2CH, and that's more acidic than this SP3CH. Well, let's consider the conjugate bases. Conjugate base would be this anion here. Okay? And let's consider the one way over here, that, which is more stable. Well, they're both carbons, so there's no difference in electronegativity. So what's the argument here?
The p orbitals, the pi bonds on the other carbon make it more stable.
But why? What type of orbital is this in? That is in an SP orbital, not in a p orbital. I don't know if you were saying it's conjugated. That lone pair.
No, I was just thinking because it has pi orbitals on it, the triple bond between the two carbons would make that more stable if it was negative.
Why? Why? The answer is not resonance because it's on a p orbital.
Right.
Now I want you to explain why. What about that isn't there? I mean, maybe you can make an argument, but that's what you need to do. This one over here is sp3. There's no resonance with either of these. The difference is hybridization. Okay? Which is going to be more stable, lone pair in an sp or an sp3? Sp, more S character. Okay? All right, 50% S. That's less percent S. That means the electron is closer to the nucleus. More S character, closer to the nucleus. That's better, closer to mama. Okay? Further the electrons are away, less stable. Because that's charge separation. The nucleus is positive. The more you pull the electrons away, it's not as good. Closer to mama is better. It's just a plain hybridization effect. There's no resonance here. Question?
So would this effect be greater in stability than all the other effects that we looked at?
No, I think, no.
So resonance effect would still be the greatest?
Resonance is, well, I had to say, I said resonance is very important. You should know them all. It's in the context of the question, okay? Here, the answer is a hybridization effect. I didn't mix the other effects in here. I showed you a precise example where hybridization is the answer. Okay? Lone pair closer to mama. Okay? We got to know hybridization and then talk about that. Bases. Okay, please look at that. Bases are going to be just the opposite. Bases, you want high electron density. Guess what? We'll use the same 1 through 4 arguments. We're just going to kind of turn it around. Have a good day, guys. Have a good day. Solubility video.